Okay, so as I mentioned, as you guys trickled in, today's topic is really important and really interesting, and I'm actually really excited to begin this. Before I start, I will say I will be posting a homework. I've been trying to go light on the homework as we get in this project, but there's one that I got to post to cover some of the flip-flop timing, some of the advanced ideas for flip-flops. So be on the lookout for that homework to get posted shortly. And then I will save some time at the end of this lecture to go hand out the exams and talk about some of the things that we saw go wrong. Everybody's exam grades should be posted. I'll talk more about that when we get there. So today we're talking about something we're in chapter 14, and they're called state machines. Now, a state machine is one of the most important parts in all digital logic. So far, everything we've designed is part of what we would call the data path. So you're going to break down all digital systems, more or less, into two concepts of data path and controller. So the data path is what do we do with the data? The controller is the brains of the thing. How does the thing think? How does it decide what it's doing? Now, how it decides, well, you write a program to do it. The structure we almost always use for writing the controller is called a state machine. In fact, we use them in data paths too, for many reasons. They're just ubiquitous. So what is a state machine? Well, first off, what is a state? The state is, how does the book define it? A description of the condition of a system at a given time. But in other words, what is this system doing right now, right? So the example that I like to use is a stoplight. The stoplight has essentially three output states that we can see: red, yellow, green. And there are conditions that transition us between red, yellow, and green in a defined order at a given time, right? So that's all a state machine is saying go from red to green if this. You can represent all of these states as Boolean variables. So I could say the state is red, but I could also say the state red is equal to 0, 0. So state 0 is red. Green would be, let's say, 0, 1. And yellow is 1, 0. Now, we're going to get into some simple rules of assigning state numbers, and I have kind of violated them here. But we'll come back and use this as an example. So when we want to describe these, right, it's helpful to think through state diagrams. And in fact, whenever I design a complicated system, the first thing I do is I draw something that is called a state diagram. So if I want to have states of red, of a stoplight, I start by saying, let's be in red. I want that to be my default state. So you could add an arrow that just says, on startup, let's enter red. Well, red then wants to go to green. When does it go to green? Well, let's say that this is a simple stoplight, and the only thing that it's detecting for is, let's say it has a pressure plate, right? Car pulls up and measures some weight, it flips. So then we would just have to be able to write, well, you'll see a couple of different ways of doing it, and they're all valid. So let's say I could write P is equal to 1. Right? So if P is equal to 1, if this is true, So if pressure got detected, move to green. Then green hangs out here. So we're going to say, well, I have a timer T. So if not, timer. So this is the other way of writing it, where I just write the variable and put a bar over it, or not, right? So I'm describing the variable that determines whether this is flipped or not. I go to yellow after timer. And then I go back to red after timer. And we can differentiate these timers. This is timer yellow, right? If we wanted. Again, we don't want to. So there's like the minimalist approach where you can do something like, well, I'm in yellow unless, right? I just write the condition. A proper state machine will address all possible conditions. So this is determined by timer, not timer, right? If I don't draw this one, it's implied, but it is proper to write that. Now red is missing its not pressure, right? So this is a bare bones state machine diagram. I am missing something else though. I am missing the outputs. So right now the names imply that there is an output. But that's not how we do that. We don't give it names because I could just as well have this up there and call this 0, 0, 0, 1, 1, 0, right? So then how do I know what my states are? Well, I do this notation, dash red, where this is my state, this is my output. Dash green, dash yellow. So my outputs are declared in those states. Now, this state machine is a particular type of state machine called a Moore state machine. So the two types of state machines are Moore and Mealy. And you will ultimately, I will warn you, you can mix these two types of state machines, but for the starters, we'll keep them separate. What a Moore state machine means is that my outputs are determined strictly by the state that I'm in. Now, Mealy state machines are a little bit different in that they are determined not only by the current state that you're in, but also by the inputs. So the book gives this example where it's just kind of a generic A, B, C. It has a loop back, it has a transition, has a loop back. All right, this is figure 14-1 if you just want to look it up soon. But I will draw it in its entirety. All right. So now you'll notice I don't have, so this is the completed state machine, it's proper, and it has no outputs inside of the states. Instead, you'll notice the dash notation is outside. So what this says is if I'm in state A and my input is 0, I output a 1. So what this is saying is that it has an input / output. Now this one is a strictly proper state machine in that all inputs and outputs are declared in every single state. So if we flash back here, that's not true, right? Because I have pressure and timer. Now, in fact, I have two different timers. I have T and TY. If I wanted to be strictly proper on this one, my transition would have to look like something which is timer, don't care, don't care. Where this is timer, this is pressure, timer Y. And then this transition then would be don't care, TY. Right? So you will see these shorthanded ways where I only address the variables of interest. So let's flash back to this one. How do I do that? Well, this only has one input. And I could, instead of having that input is 1 or that input is 0, I can replace it with the Boolean variables. So if I'm in state B and I get a 1 on the input, I output Z and go to state A. Now, we could have a situation where, let's say C, no matter what, we're just going to hit C, and the next transition, we're always going to go back to B. In that case, I can use a don't care. In a transition state diagram, we don't use X for don't care. We use a dash. So when I transition out of C, I do it regardless because I don't care what the input is, but the output should be 0. Or we could write it as not Z. Similarly, if we call our input A, instead of having a 1, I could have A or not A, right? That's also viable. I'm particular to using the variable notation and sticking to only the variables that I care about for that state, because it keeps it a little cleaner and simpler. So the main takeaway is, whether we're more or mealy, the notation is input / outputs. Does everyone get that so far? Any confusion so far? Okay. So we can go and complicate things further, like we always do in engineering courses, and we can write up what we call a state transition table. So that transition table, I think we can all hold this idea in our head. Well, I'm going to erase this. Okay, so let's use this Mealy state machine as our example for the moment. So if I am currently in A, I need to make a decision of what my next state is. Well, my next state has, So I'm going to backpedal on this just to change this up. Instead of having our input be A, we're going to call it W, because otherwise I have an input A and a state A, and that gets confusing. Okay. Now I can decide what my next state is based on my input. If my next state is, sorry, if my input is 0, I just hang out in A. Otherwise, I go to B, right? What are my outputs? Well, if W is 0 and W is 1, if W is 0, I could say either 0 or Z, right? Let's use Z at the moment. So 0, I get Z. W1, I get Z bar. Does everyone see that?
I don't see it.
I'm in state A. I get a 0. That means I'm getting this 0, but I'm staying in state A and outputting this 1.
Okay.
The output in all of these is Z, but they can be represented as 1 or Z or Z bar.
I thought that was like the Z that we did on the mock.
Oh yeah, no. This is just yeah, this is just the output, not high impedance. This is Z's. So I use these as outputs a lot.
C in this case would be remain stay on the condition that we were working on. Not changing anything.
Z is an output, like the red light. So it's not being used in this state to determine anything. It's just a result. Okay, so if I'm in B, the two places that I can go to are A or B, right? So I'm here. This is my current state. My next state, if I get a 0, is my input.
Right, so if you're in B, you could either go to A or you could go to C.
Yes. And if I get a 0, I go to C.
Or you can stay B.
There is no option for staying in B. So if I get a 0, it's C. A 1, it's A. A 0, I output Z. Oh, wait, no, sorry. A 1, that is Z bar. And that's a 1 is a Z. C. Well, C, the only thing that it can do, as it currently is written, is go to B. And then it's just, well, the output is always not Z.
So is this, wait, is this following, so in our book?
This, I've slightly modified it.
Oh, okay. That's why you get the B.
You have to move from that state to that.
Yep.
There's no option to stay.
Yep. Now, we could extend this. So I'm not following the book exactly yet on this one, but it's the same shared ideas. Okay, so the next idea that I will introduce to you is each of these states might have multiple outputs, right? So instead of just Z, I'm going to update all of the outputs. So let's take this to a little bit more of an advanced idea and how I write it. So if you're like me and you think in active high, right? I think active high all the time. Either the output is true or it's not. I will go back and I will ignore all Z bars because I don't care, right? It's either true or it's not true. So I will just initiate, or I will call out specifically where it's true, and I will assume everywhere else it's not true. I can then have multiple outputs. So we'll call this Z0, and say that when I get to state C and I leave, whenever I leave state C, I want to assert Z2. Or wait, I guess it would be Z. Well, we'll leave it at Z2. And then say if I ever leave B into C, I'd be Z1, right? So now I have 3 potential outputs. If I were to update my state table for this, instead of writing output here like so, I would need to create one for Z0, Z1, and Z2, right? And I'd fill those in and extend that state table. Okay, so now I'm going to walk through a more complicated example. It's actually just really kind of long and kind of dull, honestly. So in your book, they talk about, let's see, a claw game state machine. Because, and this is really how you would make one of these, is you would just use some simple digital logic that had a state diagram to it, and then you turn the state diagram into a circuit, which we'll go over later. So it wants to say that it has input called coin, button, and then it has like at X home. So let's start with coin. Coin goes true when a valid coin is dropped in the coin box. Button goes true when a button is pressed. There's at X home, which is true when the X position of the claw is all the way left. At X limit is X position when the claw is all the way right. Right, so it's got all of these inputs. It's got outputs that are X right, true to make the X axis motor move the claw right. X left, make it go left. Y back, Y forward, Z up, Z down. So then they go and build a state machine for this claw, right? Which is, and you will see many, many state machines start this way, where we start in idle, which we just hang out until something happens. We leave idle if and only if coin happens. Then we're going to wait. What are we going to wait on? Well, let's first make idle proper, right? Not coin. We're going to wait. I'm just going to use B for button. We haven't pushed a button. We're just going to sit and chill. Once we push the button, it's going to go right. Let's see. I really kind of hate this one. So what this is saying is I push and hold the button and I move right as long as I hold that button. So I'm holding the button as it goes right, 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 and then I let go and it will stop wherever I am. And then after I've let go of the button, it's going to move into, they're going to call it state back. It's going to loop on button. So I'm not holding a button. It's going to output Y back. Until I push the button. So basically, the only control I have is a button, and I'm pushing and letting go,
And then it cycles
through each of the directions.
back.
Yeah.
Okay, so it's kind of not how I think of a login.
Yeah, it's not like you don't have a little joystick. You have no controller but a button.
Yeah.
Right? So this is a very right? I'm not going to walk through because that's all it's going to do until the last state. So it's going to step through the 4 directions. It's going to get to essentially what they call home. And it's going to sit and loop inside of this. If you recall the signals I talked about, which is X home and Y home. Y home or X home. So if neither one of these are not at home, I stay in that state and output X left and Y forward. Because that's the direction that it has to go in order to get home. And then after it's home, it can jump back to idle.
So this is a state machine.
Yes.
This is what.
This is a state machine describing the behavior of a claw machine that I just go button, 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 button in order to control it. Now, this one, as you guys kind of instinctively kind of tell, is silly, right? But it illustrates the idea. So here we've used names, again, just like I used red, green, yellow in the other one. And we want to assign them numbers. As I mentioned before, these states have some rules that we would prefer for assigning them numbers. So the rules are, if states have a common next state, they should be adjacent as far as numbering goes, if possible. So if I had something like that. I had a state D. The next state for D and C are different, but B and D next state have a shared next state. Right? Because both of them have a next state of A. So they should be adjacent numerically when I make these numeric assignments to these states. So instead of 0, 1, 2, 3, by this rule, it should be 0, 1, 2, 3. Okay, next rule. States that are the next state of a common state should be adjacent if possible. Well, this would be really easy to do 0, 1, 2, 3. That still fits. And then states that have the same output given the same inputs should be adjacent if possible. So if these outputs were the same, again, that makes them want to be numerically adjacent. It is normal, and you should, draw the state diagram and then worry about the numeric assignments. Because the way you draw it will make it fairly obvious what states should be adjacent numerically. And it is normal and encouraged when you start getting complicated state machines to redraw them when they start to get insane. Because sometimes you'll get ones that like are crossing over each other a million times, and you may want to parse them apart so that it's kind of a clear flow. I have a thermos that's too good at its job. It keeps my tea too hot to drink for hours.
Is this kind of like drawing state machines? Is it kind of like drawing a flow chart?
Yes, very similar to drawing a flow chart that is whose transitions are determined by Boolean logic.
So you can still like do flow chart symbols.
I don't think we cover that in this course. In 3610, we will cover that. So this is a state machine diagram. That we would call a state machine chart. And
This is kind of like in programming, where you like, I guess, is it related to?
yes. So in a state machine chart, what we would do, and we're going to revert back to the stoplight because I like it. I'm in red. I output red, right? When I leave that state, I go to a decision box, and that decision is pressure. If I have pressure, I go to green and output green. So that's my one. If I don't, I go back to red. Right? Now, we can also implement another symbol in this, which these are output boxes, and this one would be like, let's call it busy. So this would be to tell the light in the other direction that, hey, you really can't be green right now because I'm green. Right? So this is a state machine chart, which is more strictly clear than the state machine diagram. That being said, I strictly use state machine diagrams. I teach the charts in 3610 just so that if you encounter them, you'll understand them. But it's a little beyond the scope of this. Because honestly, it's unnecessary for state machines. Because more relevant for, well, you'll encounter state machines in CS courses as well as EE courses, because they're incredibly useful tools.
And can you do this state machine for a project? Is that possible?
Number 3 will be a state machine. For this one, you don't need a state machine. We just add complexity. For project 2, it just adds complexity. With the exception potentially of the process counter, but even then I would not use a state machine. Okay. So if we wanted to build a state machine out of discrete components. So the FPGA, if we program digital logic in VHDL, it will just make one for us and we don't have to worry about it. But it's good to understand what's happening, and there will be questions about this. So anytime I need to store something, right, memory, what current state I'm in, I need a register. So let's just make it a DQ flip-flop. You like those, right? Q, the output, is our current state. Then I can take this output, feed it back, and put it into what the book will call a next state decoder. That will compare what are our inputs, what is our current state, right? And output, what is our next state? Then, when a clock edge hits, we'll put next state into current state, and we've now moved into the next state. The output coder will look at whatever that is and update like ensuingly. So each clock that happens, we will evaluate what next state happens. That next state may be stay in the same state. That is determined by our next state decoder. So just as a way of looking ahead, that next state decoder is just going to be digital logic, combinational digital logic, right? So if my input, in the case of a stoplight, my input is pressure, and my current state is idle, my next state is green, right? So in that case, my next state decoder would just look like an AND gate where pressure is one input and this is current state. And if current state is idle. So, but that's only addresses one part of that decoder, right? Then we have to build up more complicated logic to cover all of our states. And we can use all the tools that we've learned, K-maps, for example, to build up what this next state decoder is. We'll go into more detail as I progress forward, but I want you guys to keep that in mind as I build up towards that. Okay. For each output that we need, each final output, we need to write a K-map in order to solve these. So let's start with a state table. This one's easy. Okay, so we have this table where we're just saying if my current state is 0, I evaluate W and put an output and go to this next state, right? We all know how to read this, hopefully. Might take a little bit, right? But we can figure it out. Now we want to figure out what is our logic for output Z. So let's draw a K-map. for that. Right? And my output is determined by what is my, oh, sorry, not Z, W. And this is the K-map for Z. So my output is determined by what is my current state and what is my input. Well, and I can start looking at that. Well, if my current state is 0, 0, and my input is 0, I get a 1. Right? Similarly, if my current state is 1, 0, which in this case I have not defined, right? So this is harking back to that ABC three-state state machine. And they've given numbers 0, 0, 0, 1, and 1, 1 as the 3 states. 1, 0 is not used, but it's still a number that exists. Yeah.
If all 3 inputs are 0, it's 1.
Yes. 0, 0. Well, if current state is 0.
Right. And then the W is.
And W is 0, Z is 1.
Right. Right.
Yeah. Okay. So this is a state that's not used, so I don't care what the outputs are at this point. I don't care what the next state is because I should never end up in this state. What that does is it frees up the ability to put don't cares into our K-map. So those two don't cares come in at the 1, 0, right? So I have 0, 0, 0, 1, 1, 1, 1, 0. So in the 1, 0 state column, I don't care. Right? And then the only other situation that I have is if I'm in 0, 1 and W is 1. So I have to be in 0, 1, W is 1. There we go. Now we could use this to simplify and make some logic for our output. Well, the only thing that we can really do, right, is that and this. Don't have a lot of simplification. We could turn that into a circuit, and now we can start plugging this into a new block that we will call our output decoder. But because we're a Mealy state machine, our outputs depend on our inputs. Right? Now my input, it gets fed forward to my output, as does my current state. And then I can output my outputs. If we were to use one of the modified ones that I did that also had output Z1 and Z2, I would need a new K-map for each of those. And I would create a new circuit for each of those. And I would combine all those circuits into one output decoder block. We feel okay so far? I guess we'll do this one. So something that I will be careful to do, or rather to avoid, is if you notice this book, I skipped over the BEMs, the variable entered maps. This book likes to use variable entered maps. I will not require you to use them. I will try and avoid homework that uses them or rewrite the homework in such a way that doesn't require them. It can simplify these next state outputs. So if you want to read the book and follow along how they use them, you're free to. They're not necessary. I'm going to look at the time and the example and see what I've got left to make sure I want to spend my time wisely. Okay, let's do Let me take a pause. Sorry. So I'm working on example 14.2. It does something that I find annoying. So they start off with this table where the current states are there, and they have columns. The columns for the inputs A and B are out of order, and they don't fill in all of the current states. If they give this to you like this and say a homework problem, the first thing to do is add the states that are necessary, fill in the don't cares, and then reorder the inputs so that they're just in order because it makes it easier to read. So I'm going to skip to that part of the solution so that we don't just all go a little bit crazy.
Why would they not do it in
Oh, they did not
order?
It says, the table is put in the binary order that it has. And then add it. So that was it. It's an example.
Why would they not do it? It's because they like to cause you grief as students. There's no real reason that this would ever happen, which is why I'm kind of skipping to this step. Okay. Oh my gosh. 1 0 1 1 0 0 0 0. They're filling in don't cares for all of this. And then they're jumping into okay. So first off, I would like to point out that I could give you a question on an exam that gives you a state table and ask you to turn the state table into a state diagram. Hopefully you can do that. It's just a matter of drawing the bubbles that are necessary, making the connections. If there's a whole bunch of don't cares, that state doesn't exist in the state diagram. If there's only a couple of don't cares, it might be that it transitions out regardless of what the inputs are. So be careful of that. Okay. So we want to evaluate the next state logic and the output logic. So let's start with the output logic because I've already addressed that, right? So what we care about on the output logic is what is our current state and what are our current inputs? So let's say Q1, Q0, that's our current states. And we have A and B. Right? We need a K-map. For the output, we need an output that is determined by all 4 of these variables. If we were to go start filling through, I could say that, well, in the case of 0, 1s, all of my outputs are don't care. So don't care, don't care, don't care, don't care. Right? Now what we can see from that is that each of my columns is going to be a row of AB. So we can pretty quickly jump to, well, in the case of 0, 0, I do 0, 1, 0, 1. 0, 1, 0, 1, right? Because they're out of order. And then I can just jump down to the same thing, 1, 1, 1, 0. 1, 1, 1, 0. Last one, 1, 1, 0, 0. 1, 1, 0, 0. And then I can just start circling things, right? So I'll switch to a different color real quick, just to give you guys a little bit of a K-map refresher, right? We want to start looking for implicants, or I'll call that vocabulary word, that are big. Well, we have this nice big square. Ooh, that's a terrible marker. Squares, we like squares. Square, that's a good one. This one? Oh, here. Good call.
Could you also do, I mean, if you didn't see that, could you do just the two bottom ones?
You would, you just end up with non-minimal logic.
Yeah. Okay.
And then you'd miss a point on the exam. So we've got 3 implicants, which means we're going to have 3 AND gates going into an OR gate, right? I'm not going to fill those out, but that's what you would end up with. I won't actually draw it as your circuit. Now, I don't think the book does this yet, and it drives me a little crazy. So we're going to do it now without the book's help. I would like to point out, if you recall the picture that I drew before, there is an output decoder. We just solved that. What about the next state decoder? What does the next state depend on? Well, the next state depends on the current state and the inputs. So it turns out the K-maps drawing is the same, but instead of the outputs, we fill it in with the next states. Now this is where the thems actually comes in a little bit handy. But we'll do it without. So if we just implemented this directly, you're going to start seeing a problem pretty quickly, right? So if I have current state is 0, 0, and AB is 0, 0, my next state is 1, 0. Well, that's a problem unless we start using VEMs, right? We don't want to use VEMs because I don't like teaching them. I never use them. What is an alternate that I could do? Well, what I would do is instead of writing the next state in here, I would write 2 K-maps. One of them for Q1 plus, right? And then another one for Q0 plus, meaning the next Q1 and the next Q0. So this is essentially 2 outputs that are dependent upon the inputs. So when I need 2 outputs, I need 2 K-maps. This is a perfectly fine way to do it. But given that this is Q1 plus, right, the next Q, do you guys think that you could go in and fill out this K-map?
Just knowing that the second thing.
Yeah, so let's start off with Q1 plus. First off, we have a whole row of don't cares, regardless of Q1 or Q0. So my 0, 1s are still straight up don't cares. My 0, 0s then, if I'm dealing with Q1 plus in the next state, 1, 1, 0, 0. Does everyone see that? 1, 1, 0, 0. Similarly, 1, 1, 0, 1. Oh, whoop. 0, 0, 1, 1.
So we have Q1 and Q0, like the top row.
This is just Q, yeah. So this is Q1 and Q0 of the current state.
Okay.
And Q1 plus of the next state is our output.
Now, A3 or
A and B.
Okay.
So then I can solve this one, and I have bit 1 of my next state. I would then draw another circuit for bit 0, and now this is how I make my next state decoder. It's 1 bit of the next state at a time. Okay, so that only leaves me 15 minutes, so I'm going to stop there. We'll come back, we'll talk more about state machines, and we will talk more about ultimately the delays through that next state decoder logic. Because we've talked about the setup and hold times, this can cause issues on the timing. Landon. Jacob. Jacob what? Yeah. I only got more than 1 Jacob. Okay, Sean. It's not here. Brooks. Jared. Trenton. Andrew. And Zachary. Will you take it online? Yeah. Okay. So, I did post some statistics online about how people did. Ultimately, I didn't need any curve. You guys did really well. The downside is that you're almost split into 2 camps of those that got it and those that didn't. If you fall into the camp of didn't quite get it, feel free to ask questions. I only have 15 minutes to go through this, so I will cover what I can of issues and hopefully address some of them. So the first one was just look it up in the book. If you missed that and the book is like wrong or something, because I may have a different version of the book than you, which is terrible. If that's the case, come talk to me and show me your book and we'll get some more points, but it really is just pull those numbers out of the book. The other ones, right, the true falses, they're pretty self-explanatory if you didn't get it because it's the other one. The order of concurrent statements does not matter, but the order of sequential statements does. Yes, sequential means sequence, right? Concurrent is combinational, it can go in any order. Let's see, skipping ahead. I think most people got 6, 7, 8.
What is 6?
What problem can occur if an input to a flip-flop changes at nearly the same time as the clock goes high? The short answer, the quickest way to answer that is it's just a race condition. The full answer, if you're elaborating more, is that you don't know what the output is going to be when that clock hits. It could be any. It could be right? You don't know. Number 8. This was just asking to use the ones that we talked about in class. So the one of them is the gated clock, where you use an AND gate, say enable AND this. That's the wrong way of doing it. The other way is we use a mux that feeds back from the Q into D or the new value. And if you're enabled, you bring in the new value. If you're not enabled, you just feed back that Q and you lock on regardless of what clock is doing. Five, a lot of people miss this. I should probably talk more about flip-flops, but the T flip-flop, if T is high and there's a rising edge of the clock, not both edges, that was a common mistake, it's rising edge, then it toggles or flips. So a rising edge, so basically the first clock positive edge does nothing. The second positive edge flips it from a 0 to a 1. The third flips it from a 1 to a 0. And then the fourth one does nothing, right? Because it's no longer T.
you draw that out for me? I have a hard time doing that. I understand every other flip-flop except T flip-flops. Does the T stand for toggle?
Yeah.
Makes sense.
Clock, T.
So now on the problem, the T went up, right, as the clock went down.
Doesn't matter.
Okay.
Right. It doesn't matter as long as this rising edge is true or happens while toggle is true.
Okay.
So this could happen anywhere in this region.
Just can it happen at the exact same time?
No, because then it would be, who knows, right? Because we failed to set up and hold time. Okay, so we come along. I mark out the points of potential interest. I find that there are really only two because toggle is true. If toggle is not true, nothing happens. I come along, I start out at 0. Toggle isn't true, so nothing happens. Toggle is true, so I flip. Toggle is true, so I flip. Toggle isn't true, so I stay.
Oh, so just toggle on the rising edge, not rising and falling.
Correct.
Okay.
Next one's the devices. D flip-flop, JK flip-flop, mux, and a full adder. The full adder I accepted lots of different versions. If you just wrote adder, it was probably fine. You wrote full adder, it's fine. Number 11, write logic equations for a full subtractor, including a truth table. So some people missed because they would write out the truth table. Some people didn't write the truth table despite saying, I said show your work. The next step of it is a K-map. If you wrote the output equation that you got after a K-map without writing the K-map, you missed a step in showing your work. You missed points. B, draw a schematic symbol, not the gates, for the full subtractor. So that was just asking, draw a block, call it a full sub, give it the inputs and outputs. Next one is connect those up together to show a full subtractor. Most of you got this one right, which good job. Yes, I know. I like to reward people for doing homework sometimes, you know. I don't feel bad about that one at all. So, well, I feel a little bad if you guys missed some points, but okay. 12. This one is the hard question by my estimate. So the way I write exams is almost always lots of easy ones, couple of medium ones, and a hard one. This is the hard one. The hard part of this is not that the question is hard. The hard part is that you needed to read all of the instructions and follow them, right? But that's part of digital systems, their digital circuits, is reading and understanding and turning that into something. So in the above code, there are errors. Identify and correct at least 3 of them. Most people got this because there's like 7 errors in this. The only people that missed it were ones that assumed that something was an error that wasn't, and then only marked down 2 of them. Examples of things that aren't errors is one of my down 2s isn't capitalized and one of them is. That's totally fine. It's not case sensitive for that. Yeah, most people got these, yeah, did some weird things, yeah.
So if you mark down 3 correct things and a couple of non-correct things, you still have.
Yes. Yeah, because you can't just like everything is wrong and expect points, right? It should be a small amount of points as long as you did it though. The next one, draw a block diagram of the internal connections for the 3 required add or sub modules. Now, this one confused a lot of people. Add or sub was a component that was given to you in the statement saying that it takes a 4-bit standard logic vector, vec in an input add sub that adds 1 if add sub is 1, or subtracts if add sub is 0, then passes a 4-bit output vector vec out. Has two other outputs, OF and OE, that are raised when adding 1 to 111 or subtracting 1 from 000. Okay, so this question was really addressing your ability to read that sentence and turn it into something. So this is just saying, I'm just going to label these as add or sub, shorthand it, add sub. So it's taking the port vec in, vec out, wiring those up, right? Each one of these has an add or sub. What did I call that port? Add sub. I'll write that out. Add sub input. Okay. So all I'm doing is stepping through my add or subs, addressing what those ports are and figuring out how they're connected. So the output of the first one goes to the input of the second one and so on and so forth, just like your full adders. They're all doing the same operation, add sub. I may have called that something else, but then they all have over full and over empty outputs. If we ever add 1 to these, we want an error. So I defined error, right, that asserts if we ever add 1 to 111 or subtract 0 from 00. You don't have to worry about them doing, just know that that's what these flags do. Well, all of these, and I'm just going to combine these into one. There's a couple different ways you could do this. Right? If I take the or, if it's OF or OE, or OF or OE, or OF or OE, or then I get an error. Missing this OR gate and just drawing them all together was the most common issue on this problem. On writing the VHDL declaration component for add or sub, a lot of people miss this one, and I don't know where the disconnect was. I suspect it was you didn't read the instructions where I gave you all of the ports, inputs, and outputs for add or sub. I didn't expect this one to be a problem. I really expect this one to be like gimme points, but it wasn't that way. People were like mapping errors and that kind of thing. You just didn't map the component that I provided you. The next one is write a VHDL statement that writes the inputs or outputs of one or more adder subcomponents to assert the error when any of the adder submodules assert OF or OE. This again was supposed to be a give me problem and provide a hint that you needed this gate. So I was thinking that like, all right, you guys might, I was expecting you guys to miss over this OR gate and then get to this problem and go, oh, that's what the error does, right? That was my hope. That's not quite what happened. All you have to do is write an OR statement that uses all of those OFs.
What if you did an if?
You, depending how you wrote it, you may have gotten partial points. As long as it did it. But a lot of people did write if statements and then miswrote the if statement. Next one, write VHDL instantiation of the second of the 3 add or sub modules. Well, a lot of people miss this, but now that you can kind of see what that is, I think you can see how those connections are, right? The main one being that I told you to use this as pass vector, right? And then this was pass vector 1. So then you would just write that instantiation using pass vector. 4, what device should we use in project 2 to create the accumulator? This was, if you did the lab, it's straightforward, right? D flip-flops. When are my office hours? Fortunately, I don't think anybody missed that one. The last one, again, another just like, here's some free points, yet it was missed. Write gray code. That's all I was asking. Some people just wrote binary, and that was not good. So the main takeaway from that is read the instructions. I honestly feel like the majority of points missed on this exam came from people not sufficiently reading the question. We're pretty much out of time, but I will answer any questions that anyone has. If you have specific questions that you don't want to ask in front of the class, you can come up or meet me in my office hours tomorrow. Make sure you guys are all getting your homework turned in, because I would hate for you to fail the class just because you didn't turn stuff in, and I'm pretty lenient with the due dates.
So
right.
We have a homework assignment due. I haven't looked at it.
I haven't posted it yet. I will be posting one for flip-flops.
What did you say before that?
I don't remember. Oh, I was just saying, don't fail the class or do poorly just because you didn't turn stuff in. That's my least favorite reason for someone to miss points.
Yeah.